Oliveira. He will talk about three-dimensional Navier-Stokes simulation of hill-saw flows using finite difference schemes.
Thank you. This is part of the work that I did during my PhD studies at the University of California in Santa Barbara. We're going to start just showing some motivation from the oil industry before introducing the Safran-Taylor instability. Then we present traditional two-dimensional gap average modeling and compare some 3D results and take this comparison as our academic motivation. Then we go on to show governing equations, boundary conditions, talk about the discretization of the code and validation. And on the results, we will focus more on the inner splitting instability, which is intrinsically three-dimensional instability that hadn't been described previously, although this kind of problems has been under study for over 50 years. This is a movie downloaded from YouTube, made by Tech Oil, basically showing typical processes used in oil extraction. So basically, we simply take water, pump into the reservoir to displace the oil. But this displacement is not well behaved, as the picture shows. In fact, if it were, I wouldn't have any talk to give. So what really happens whenever we have a less viscous fluid displacing a more viscous one, the interface between the two can become unstable. And this instability gives rise to the viscous fingering. This process occurs for miscible and for immiscible flows. And for the oil industries, both cases are of relevance. Instead of water, in many cases, carbon dioxide is pumped into the well. This porous media flows is, in most cases, modeled using a Hilly-Shaw apparatus, which simply consists of two solid plates put closely together. And as the motion is primarily bidimensional, most people take an average across the gap of the Hilly-Shaw cell and neglect the whole structure that the interface between the two fluids form across this direction. This two-dimensional law is known as Darcy's law, and it can be easily derived from the Stokes equations. It has been highly successful describing this kind of flows. For example, predicting the existence of tip splitting instabilities. But here you want to focus on the importance of the gap direction, and we'll see that it forms this inner splitting instability that splits the finger lengthwise, leaving the tip intact. For that, we use the three-dimensional Navier-Stokes equations, here written with index notations. The viscosity mu is given as an exponential function of the concentration field. This concentration measures the miscibility of the more viscous fluid. So it's 0 on the left end of the domain, 1 on the right end, and any value in between is just a measure of the interface. We basically take concentration 0.5 as the interface between the two fluids. It's governed by this convection diffusion equation that give us a total of 3 main governing parameters: a viscosity ratio, the Reynolds number, written in terms of the gap width, and the inflow Poiseuille velocity, and a Peclet number. We impose no-slip boundary conditions on top and bottom walls, symmetry conditions on the side boundaries. Again, we impose a Poiseuille inflow condition, and the concentration field satisfies an error function, and we impose a convective outflow for the 3 components of velocity and the concentration field. For the discretization, we use a Stargate grid. Again, the code is in 3D, but here we just show a schematic of a two-dimensional Stargate grid. The scalar variables we place at the cell centers, and the vector variables at the sides. For the discretization of the diffusive terms, we simply employ the first divided difference, and for the derivative of the convective terms, we use a fifth order weighted Inouye scheme, which basically takes the weighting of 3 third order polynomial interpolants. The scheme that we use in the integration is a hybrid scheme between Crank-Nicolson and Runge-Kutta. The Crank-Nicolson basically evaluates the diffusive terms at old and new time steps. So taking all the terms of the new time steps to the left-hand side, that leaves us with a system of tridiagonal equations. And third order Runge-Kutta schemes, it simply computes 3 predictions of the derivative and weights them in order to advance forward in time. So if we write the first component of our momentum equation here to try to discretize using both of the above schemes, here we see the Runge-Kutta scheme immediately, and the weighting of the predictor steps is done by the alpha and gamma parameters. Here are the explicit terms, the pressure gradient, and other explicit terms coming from the diffusive terms are inside this age term. And the remaining diffusive terms, we employ the Crank-Nicolson time step n on the superscript is all the values that are known, and a is the unknown that accounts for the first step of the Runge-Kutta integration. To close the problem, this equation needs to be combined with these two, and we'll talk about that in a second. But applying the Crank-Nicolson to the above discretization, we need to take all the unknown terms to the right-hand side, and using this factorization approximation method that is still second order, that leaves us with 3 tridiagonal systems of equations to solve. And after we integrate for this term, for this velocity difference, that gives us an intermediate velocity, and we use a Helmholtz decomposition and adjust the pressure to project this intermediate velocity onto the divergence-free velocity field. And that's what those 2 equations do. Combining them, that give us this Poisson equation that we need to solve for this scalar phi that is related to our pressure field. And after we solve this Poisson equation, we can update the pressure gradient, and we'll have finished the first integration of the Runge-Kutta, the first step of the Runge-Kutta integration. So to validate the implementation of this code, we advance this base state in time and calculate its front thickness, d. After a transient regime, it obtains a quasi-steady value that is plotted here against the Peclet number for 2 different values of the viscosity ratio. Our results are in the continuous line, and the dashed lines are the Stokes calculations, 3-dimensional Stokes calculation, and they agree within error below 2%. Our Reynolds number is kept small at 1, so the 2 theories should agree pretty well. We also measure the front velocity that is plotted here, and the comparison to the Stokes results is also very good. In a second step for validation, we impose wave perturbation to the base state with a wavelength of maximum growth and a small amplitude to ensure that we remain in the linear regime for some time. With that, we can calculate some growth rates and compare against linear stability theory based on the three-dimensional Stokes equations. Again, the comparison of the two theories is also gives errors under 2%. But now the question becomes, how does these growth rates compare against the growth rates computed using Darcy's law or other theories that employ a gap averaging approach? And that's what this plot shows, the maximum growth rate with increasing viscosity ratio for two values of the Peclet number. And we see that the two theories only agree for small values of the governing parameters. And that's another motivation for our work. If at a linear regime, we have a good discrepancy between three-dimensional modeling and gap average models, we want to go through a 3D linear regime and see how that can add to our knowledge of these systems. This is our first simulation with Peclet number 1000 and viscosity ratio in exponential scale 3. As expected, smooth diffusive finger grows, but as the projections of the symmetry planes indicate, something is going on inside the finger, and that's exactly the inner splitting that I had mentioned previously. What drives the formation of this instability? We see that the thickness of the interface becomes thinner and thinner with time, and eventually leading to a pinch-off. When that happens is when the inner splitting is characterized. This is driven by the presence of a component of vorticity along the direction of the flow. So this is just a concentration contours in the mid-gap plane, and looking at streamwise cross-sections through this area, from these locations, we see that near the tip, the flow simply looks like a source flow, but any distance behind the tip, we find the presence of a streamwise quadrupoles that brings fluid from top and bottom walls towards the mid-gap plane and displace them towards the side boundaries. If we increase this spanwise domain and simulate the evolution of wider fingers, then we find superposition of the tip splitting instability that is well known with our predicted inner splitting instability. And if we impose a random perturbation in a much wider domain, then we see the interaction of many fingers. Initially, 10 fingers grow, but the fastest growth of the adjacent ones shield the growth of these two. Here we see the merging of two fingers, another merging here, eventually leaving us with only 6 fronts. And if we wait a little bit, then the inner splitting will appear in all of these fronts. Initially here, then another one here, followed by this one and the other 3. We have found experimental evidence that this inner splitting appears in experiments. This is an experiment done by Tony Marksworthy trying to characterize the inner splitting. I don't know if you can see well, but there is a lighter band bisecting the finger, and this is a picture of the experiment done by Udin in '69 under the influence of gravity. And here we see a lighter band bisecting dark fingers, and also a darker band bisecting the light fingers. And just a brief summary, and thank you very much.